Okay, so now basically we have another two matrices. For example, A is a matrix of a square matrix of 6, 9, 2, 3, 6, 9, 2, 3, and B is a matrix of 2, 6, 0, 7, 9, 8, and now the matrix you want to find, basically find AB, right? The multiplication of the product of A and B. So first of all, you need to know whether AB is defined or not. So this matrix is a 2 by 2 matrix. This is a 2 by 3 matrix. Therefore, basically this 2 is equal to this 2. And therefore AB is defined. Since AB is defined, you can write basically AB is equal to basically 6, 9, 2, 3, the first matrix, times 2, 6, 0, 7, 9, 8, and then basically the matrix that you will get is 2 by 3, this 2 and this 3 over here. So you would get a matrix something like this, right? Which means that, or not something, but exactly a matrix of the same order. Which means that basically you have to always start from the first row and go through all of the columns that you find. Meaning that the first row, first you pick the first row over here, and you will stay here and first go to the first column, then to the second column, and then to the third column, and you write the results of all of those calculations here, here, and here. Second, you go to the second column, the second row, and then again you have to go to the first column, the second column, and the third column, and then you write the results of those calculations here, here, and here, and then that becomes a 2 by 3 matrix, right? So that's basically what you will always do, which is of course pretty simple, but as again you need to be careful, because sometimes sometimes I make mistakes in matrix multiplication and calculation. So I have to, so now I will start with the first row and the first column. So 6 times 2 is equal to 12, and 6 times 2 is equal to 9 times 7 is equal to 63. Now I will go to the second column, which is 6 times 6 is equal to 36, plus, so this times this, 9 times 9 is equal to 81, and then this row times this column is 6 times 0 is equal to 0, and 9 times 8 is equal to 72, right? Now I will move to the second row and the first column. The second row would be 2 times 2 is equal to 4, plus 3 times 7 is equal to 21. Then I will move to the second column, which is 2 times 6 is equal to 12, plus 3 times 9 is equal to 27. And now I move to the third column, which is 2 times 0 is equal to 0. And 3 times 8 is equal to 24. Now this is equal to 75. This is equal to 75. And there you have 111 36 plus 81 is basically a 7, and that is 117, right? That is 117. That is a 72, 25, and 27 plus 10 is equal to 37, 39, and that's a 24. That is your matrix. 75, 117, 72, 25, 39, and 24 is the correct answer. Now, as a remark, we have if AB is defined, then BA need not be defined. Meaning that, for example, if we have this matrix A here and matrix B here, and we checked here and AB was defined. So we did the calculation and we got the matrix as well. If AB is defined, then of course you cannot say that BA is also necessarily defined. BA might be defined, might not be defined, depends on the case. But I suppose if both of A and B are square matrices, then if AB is defined, then BA is going to be defined as well, because suppose that you have this matrix over here, for example, a 3 by 3 matrix, right? You have a 3 by 3 matrix, and then you have a 3 by 3 matrix. So if AB is defined, BA is defined as well, meaning that if the two matrices are two matrices of two square matrices, for example, of the same order, then AB is defined and BA is always also defined. Now, but let's see what we have in the remark. Here in this example, AB is defined, but BA is not defined, because B has 3 columns while A has only 2 rows. If I were to basically calculate BA over here, BA would be a matrix of order 2 by 3, and basically A would be a matrix of order 2 by 2, and so of course 3 and 2 would not match, and therefore BA would not be defined, of course. Now so you can say that if A and B are respectively M by N and K by L matrices, then both AB and BA are defined if and only if N is equal to K and L is equal to M. That's actually what I said, but this is of course a much better way of saying it. So you can say that if AB are respectively, you can say that if A and B are respectively M by N and K by L matrices, then both AB and BA and BA are defined if and only if which is important, we will talk about it, if N is equal to K and M is equal to, and if basically N is equal to K and also L is equal to M. Now in particular, we will come back here. In particular, if both A and B are square matrices, if both A and B are square matrices of the same order, then both A and B and BA are defined. That's what I said. But now let's go back over here. So let's see. Of the same order, then both AB and BA are defined. Right? So the second part is clear. It says that in particular, if both A and B are square matrices of the same order, then meaning that, for example, both A and B are square matrices of the order 2 or the order 3 or 4 or whatever the order might be, then both A and B and BA are defined because, of course, for example, suppose that A is a 2 by 2 matrix and, for example, B is a 2 by 2 matrix. Then AB would be, when you want to multiply A by B, 2 and 2 match together, and then again B is 2 by 2 and A is 2 by 2, and then again these two will match together. So both A and B and BA are defined. So we have no problem there. Now, over here, we are saying that if A and B are respectively, if A is a matrix of the order m by n, and B is a matrix of the order k by l, then both A and B, AB and BA are defined if and only if n is equal to k. So, of course, if n is equal to k, then you can say that if n is equal to k, then, of course, AB is defined. If AB is defined. Moreover, if I write this the other way around, meaning that if I write this as B k by L and A m by n, then of course BA is defined if L is equal to m, because this is the number of columns, this is the number of rows. So then you can say that if L is equal to m, then BA is defined. Right? Then BA is defined. Therefore, I can say that if n is equal to k and L is equal to m, and if A and B are these two matrices with these orders, then basically AB and BA are both defined, right? Are both defined. And as a result, but then this statement is a little bit different. It says that if A and B are respectively these two matrices with these orders, then both AB and BA are defined if and only if basically, if and only if this is the case. Meaning that if this is the case, then basically A and B are, then you can conclude that A and B are basically matrices of the order m by n and k by l respectively, and also meaning that you can say that, I don't know how to phrase my statement. It's a little bit complicated statement. So when I say that if A and B are respectively these two matrices, then these two are both defined if and only if that is the case. So what that means is that Now if I take this as some statement P, I take this as a statement P, and I take this as a statement Q, right? So what I'm saying here is that P if and only if Q, right? What this means is that P implies Q and also Q implies P. What that means is that if I say P implies Q, what that means is that if both AB and BA are defined, then that is the case, meaning N is equal to K and L is equal to M, right? And Q then P, or Q implies P, means that if N is equal to K and L is equal to M, then both AB and BA are defined. Now when you say P if and only if Q, or when you say P only if Q, what that means is that this is a biconditional, meaning that P implies Q and also Q implies P simultaneously. So that's what that means. Which is of course a topic in and of itself in mathematical logic, which of course I suppose you have done already in class 10 or 11 or something, or somewhere like that. That is basically that, okay? Now, so we understood all of this. And the next part that we have is non-commutativity of multiplication of matrices. Now here we have an example that even if AB and BA are both defined, it's not necessary that AB and BA are equal, meaning that matrix multiplication is not commutative. It might be possible that AB is defined, BA is defined, meaning that you can actually do multiplication both ways, but the results are not necessarily going to be the same thing. Yeah, I mean, in most cases, you would not get the same result, of course. I think it's very rare that you would get the same results if you try to, if you arrange your matrices in such a way that they gave you basically the same results. Otherwise, it actually might never actually happen. I've never actually seen such a thing in my whole life in mathematics. But of course, well, my life in mathematics has not been very long, actually. My life in mathematics has been long enough, but my life in matrices have not been still long enough, so I cannot talk about that. So, now let me take a few minutes rest, and we will then go through an example over here together. Okay, so now about the non-commutativity, commutativity of multiplication of matrices. So, as we discussed before, so we said that even if, suppose that basically you have basically two matrices two matrices A and B, AB and BA are both defined. And BA are both defined. Okay. It is not necessary, of course, it is not necessary that AB is equal to BA. That's basically what the whole story is. And we will see that through this example. For example, you have A is equal to a matrix of 2 by 3, which is, for example, 1, -2 and 3, and -4, 2 and 5. And then you have B as a matrix as 2, 3, 4, 5, and 2, 1. And to find A times AB is equal to basically 1, -2, 3, -4, 2, 5 times B, which is equal to 2, 3, 4, 5, 2, 1. And I will start with basically this row and this column. So 1 times 2, so I will get basically this is a 2 by 3 matrix. This is a 3 by 2 matrix. So I will have a 2 by 2 matrix, right? So a 2 by 2 matrix means that 1 times 2 is equal to 2. So I'm going this row and this column. So 1 times 2 is equal to 2. -2 times 4 is equal to -8. And 3 times 2 is equal to 6. Then you have this row times this column, which is 1 times 3 is equal to 3. -2 times 5 is equal to +10. And 3 times 1 is equal to 3. Then I have this row. Then I have this row and this column. So -2 times 4 is equal to -8. Plus 2 times 4 is equal to 8. And 5 times 2 is equal to 10. Then this row and this column. 4 times 3 is -4 times 3 is equal to -12. And 2 times 5 is equal to 10. And 5 times 1 is equal to 5. And that is equal to basically 6 plus 2 is equal to 8. 8 minus 8 is equal to 0. 3 plus 3 is equal to 6. That's a -4. That's a 10. And that's a basically 15 minus 12 is equal to 3. So that is 8 times B. 0, -4, 10, 3. Now B times A is equal to 2, 3, 4, 5, 2, 1 times 1, -2, 3, -4, 2, 5. This is a 3 by 2 matrix. This is a 2 by 3 matrix. That means that you will get a 3 by 3 matrix, which gives us, so I will start with basically this row and this column. 2 times 1 is equal to 2, and 3 times -4 is equal to -12. Then this row and this column, so 2 times -2 is equal to -4, and 3 times 2 is equal to 6, and then you have 2 times 3 is equal to 6, and 3 times 5 is equal to 15, and then you have, basically we said that it's a 3 by 3 matrix, meaning that you have 3 rows and 3 columns. So so then I will start with basically this row, and I suppose did I do anything wrong? 2 times 3 is equal to 6, 3 times 5 is equal to 15. So this is already, I have done this already, right? So I move to this row and to this column, which I will write here. So 4 times 1 is equal to 4, and 5 times -4 is equal to negative 20. And then this row times this column is 4 times 2 is equal to -8 plus 5 times 2 is equal to 10. And then 4 times 3, you need to be careful not to miss these markings, otherwise you will lose where you are, right? So 4 times 3 is equal to 12, plus basically 5 times 7 is equal to 25. And then I will move to this row and this column. So 2 times 1 is equal to 2, and 1 times -4 is equal to -4. And then you have the same row, this column, so 2 times -2 is equal to -4 plus 1 times 2 is equal to 2. And then this column, 2 times 3 is equal to 6, and 1 times 5 is equal to 5. And that is basically your matrix. That is your matrix. Now this is equal to basically 2 plus -12 is -10. 6 minus 4 is equal to 2. 15 plus 6 is equal to 21. -20 plus 4 is equal to -16. 10 minus 8 is equal to 2. 25 plus 12 is equal to 37. For -4 plus 2 is equal to -2. -4 plus 2 is equal to -2. And 6 plus 5 is equal to 11. That is basically your matrix. And that is basically BA. This is equal to BA. And as you can see, of course, AB is not equal to BA. Therefore, AB is not equal to BA. Now to check whether 221, -16, 237, -2, -211, and that the answers are correct. So basically in this example, both AB and BA are of different order, and so AB and BA is not equal to BA. But one may think that perhaps AB and BA could be the same if they were of the same order. But it's not so. Here we give an example to show that even if AB and BA are of the same order, they may not be the same, right? So let's do this example. $276. Example number 14. Let's say that example number 14. Let's say that if A is equal to, for example, this matrix as 1, 0, 0, -1, and B is the same thing as 0, 1, 1, 0, and then AB is equal to so AB is equal to basically 1, 0, 0, -1 times basically 0, 1, 1 0, which is the same thing as well, this would be 2 by 2 matrix. So I start with these two, so 1 times 0 is equal to 0, and 0 times 1 is equal to 0. Then this column would be 1 times 1 is equal to 1, 0 times 0 is equal to 0, and this row, this column, another color, and so the 0 times 0 is equal to 0, and negative 1, and then 0 times 1 is equal to 0, and that there you have a 0. So that is your matrix, which is the same thing as 0 1 negative 1 0. So that is A times B, and B times A is equal to B times A is equal to 0 1 1 0, and times 1 0 0 negative 1, and then if you start with these, you will get 0 times 1 is equal to 0, and 1 times 0 is equal to 0. Coming to this column, 0 times 0 is equal to 0, 1 times negative 1 is equal to negative 1. And then over here and here, I have 1 times 1 is equal to 1, 0 times 0 is equal to 0, and basically 1 times 0 is equal to 0, and that's a 0, and there you have your matrix, which is equal to basically 0, negative 1, 1, and 0. Which is basically, as you can see, therefore AB and BA are of the same order, but AB is not equal to BA. Okay. So therefore, matrix multiplication is not commutative. Right? Now, what this means is that, of course, in mathematics, you know about how mathematical logic works. When you say that matrix multiplication is not commutative, you might actually be able to find even thousands, even millions, even billions of pairs of matrices in which basically, in the case of which matrix multiplication is of course commutative. That's possible, right? But in mathematics, as you know, whenever, even if you find basically billions of such cases in the case of which matrix multiplication is actually commutative, even if you find one counterexample that shows that matrix multiplication is not commutative, then that means that matrix multiplication is not commutative. Okay? When you want to say that matrix multiplication is commutative, that means that matrix multiplication has to be commutative in all the different possible cases ever possible in mathematics. And that you always have to prove logically. Once you prove it logically that in the case of all possible matrices of such and such order, for example, matrix multiplication is commutative, when you prove it logically using some method of logic which is accepted in mathematics, then you can say that matrix multiplication is commutative. If you cannot prove it, you cannot say it. And again, if suppose that you find 1 million different cases in which not even that, suppose that every pair of matrices that come to mind, you test them, and it will take you a whole lifetime. You test them and you conclude that in the case of each and every one of those pairs, matrix multiplication is commutative. That still doesn't mean that matrix multiplication is commutative, because there might still be some pair where, in the case of which matrix that you can try, and then you will find, and you might find out that in the case of that pair, it doesn't work, right? So testing different cases doesn't prove anything. Proving things, well, proves everything. And proving means proving with logic, not proving with examples, not even with countless examples. Example doesn't prove anything in mathematics. Okay, so now the note that we have here is that it says that basically says that this, as a note, we have this does not mean that that AB is not equal to BA. For every pair of matrices A and B, for every pair of matrices A and B, for which AB and BA are defined, right? Are defined. For instance, suppose that you have A is equal to 1002, meaning that you have to make arrangements, make sure that it works. If you can do that, of course, it's very hard to find such examples sometimes. Sometimes it's very hard to find such examples. And sometimes it's very hard to find counter examples. So, but in a way, that's the beauty of mathematics, that it makes you to, it actually gets you to basically search every corner of your mind and think in every possible different way so that you can solve a problem. And well, of course, that's a long story. What is, I mean, how you can think how you can actually think creatively in mathematics, that's a little bit that's something that you actually cannot talk about. So then in this case, in the case of these two matrices, if you observe basically AB is equal to basically 1002 times basically 3004, which is equal to, basically you'll get a 2 by 2 matrix, and that starting from this row, this column, you'll get 1 times 3 is equal to 3 and 0, and then over here you have 1 times 0 is equal to 0 and 0, and then you have over here and over here, so 0 plus 0, and then over here you have 0 plus 8, right, which is equal to 3008. So that is AB. Now BA is equal to 3004 times 1002, which is equal to, again, starting from here and here, you have 3 and 0, and over here you have 0 and 0. 3 times 0 is 0, 0 times 2 is 0, and then you have over here and here 0 and 0, and over here you have 0 and 8. That is that, and then that is equal to 3008. 3008. So as you can see, AB is actually equal to BA. But that is just one example. So, and it seems that the multiplication of diagonal matrices of same order is commutative. So these are diagonal, both of these matrices are diagonal, meaning that basically except for the diagonal of the matrix, all of these basically, this element is 0, this element is 0, and this is the diagonal of the matrix. Again, here the diagonal is, these two elements are 0, so both are diagonal matrices. And of course both are square matrices, right? And of course when the matrix is diagonal, of course it has to be square matrix, so that's not an issue. We don't have to think about that. But the point is that this is a 2 by 2 matrix, and this is a 2 by 2 matrix, and if both of them are basically diagonal matrices of the same order, then it seems that in such cases, the matrix multiplication is actually commutative. So as a note, you can say that in the case of diagonal matrices of the same order, matrix multiplication multiplication is commutative. Matrix multiplication is commutative. Now the next topic that we have here is, which is related to the same discussion, is zero matrix as the product of two non-zero matrices. Zero matrix as the product of two non-zero matrices. Non-zero matrices. So that means that when you have two non-zero matrices and when you multiply them, then you will get a zero matrix as a result of that, something like that. Let's see what that is. So basically we know that for real numbers a and b, if ab is equal to 0, then neither a is equal to 0 then either A is equal to 0 or B is equal to 0. This need not be true for matrices. We will observe this through an example. So the point here is that we know that for real numbers A and B, for real numbers A and B, if AB is equal to 0, then you can say that either A is equal to 0 or B is equal to 0. And then it's necessarily so, there is no other way. Now for matrices, this need not be true. This need not be true. Meaning that for matrices, this is not necessarily true. Meaning that you could have two matrices, the product of those two matrices might be actually a zero matrix, but then none of those matrices could be a zero matrix, right? Now, as an example, let's say that you have a matrix A, which is 0, -1, 0, 2, and B as basically 3, 5, and 0, 0, right? Now, if I find AB here, I will have 0, -1, 0, 2, and multiply it by 3, 5, 0, 0, and that is equal to basically this row, this column, that gives me a 2 by 2 matrix, 0 plus 0, and then this times this gives me 0 plus 0, and then this times this is 0 plus 0, and this times this is going to give me 0 plus 0. As you can see, that's a zero matrix. Is equal to O, right? Which is equal to basically 0, 0, 0, 0, right? So you can see that the product of the two matrices is actually 0, although none of the matrices is a zero matrix. So what that means is that in the case of real numbers, A times real numbers A and B, for example, A times B is equal to 0, for that there is a necessary condition that either A is equal to 0 or B is equal to 0. One of them has to be 0. There is no other way. But in the case of matrices, you could have a matrix a zero matrix as a product of two matrices, which none of which could actually be zero matrices, right? Thus, if the product of two matrices is a zero matrix, it's not necessary that one of the matrices is a zero matrix, right? So that was basically I don't even remember what that was. That was basically now whatever that was, I will give it a label in the video. Now in the next video we will talk about basically properties of multiplication of matrices. So I see you in the next video. Thank you.